This lecture is on latent heat from the lab we did in class, and it's this very hidden heat that drives weather. So latent heat is hidden heat. Water has one of the highest heat capacities of all known substances. This means that it takes a lot of heat to raise the temperature of water by just 1 degree. Water thus absorbs a tremendous amount of heat from solar radiation. And furthermore, because solar radiation can penetrate water easily, large amounts of solar energy are stored in the world's oceans. Further energy is absorbed by the water as the latent heat of vaporization, which is the heat required to evaporate water or change it from a liquid to a vapor. This latent heat of vaporization is given up to the atmosphere when the water condenses to form liquid water as rain. If the rain changes to a solid in the form of snow or ice, it also releases a quantity of heat known as the latent heat of fusion. Thus, both liquid water and water vapor are important in absorbing heat from solar radiation and transporting and redistributing this heat around the planet. And here's a picture we can look at. It takes a lot of sunlight energy to heat this to a point to where the water is going to evaporate. But once it evaporates into a vapor, it eventually condenses into what we call clouds. And in the process of condensing, or condensation, it's re-giving off that heat energy, that latent heat that was stored in it. This energy is released, and this is the energy in the atmosphere that's then going to drive further weather. Remember, latent heat here is of fusion. Latent heat here is of vaporization. So the hotter an object is, the faster the motion of the molecules inside it. Thus, the heat of an object is the total energy of all the molecular motion inside the object. Heat is measured in joules. With convection, higher energy molecules are mixed with lower energy molecules. When higher energy molecules are mixed with lower energy, the molecular motion will come to an equilibrium over time. That the faster moving molecules will slow down and slow moving molecules speed up. So we get an average. And heat can be transported without changing the temperature. And this is key. We'll come back to this in a moment. Temperature, however, is a measure of the average heat or thermal energy of the molecules of a substance. Temperature is measured in degrees Celsius or Fahrenheit. So generally speaking, we're going to differentiate heat and temperature. Just adding heat increases the temperature of a substance, but not always. In other words, we can add heat to a substance and it not change temperature. We're going to call that latent heat. Anytime the temperature is changing, though, the heat or the thermal energy is changing. So we have to differentiate between what heat is and what temperature is. So let's look at this picture, latent heat. In order to melt ice, heat must be absorbed. 80 calories per gram of water. And once we get it to this liquid phase, the liquid state, if it's going to evaporate, it must absorb another 600 calories per gram. And we can skip the process of, we can actually go from a solid to a vapor in the process of sublimation. And this is where 680 calories per gram is absorbed. So we can go through these phase changes. We can go from solid to liquid to gas, or we can go from a solid to a gas directly. However, what happens if this water vapor then gives off heat? Well, if it gives off and condenses into liquid, we call that condensation, where it releases 600 calories per gram. In this case, we have liquid water. In order to freeze it, it must release another 80 calories per gram of water. And we can actually go from water vapor into solid ice in the process of deposition. And this is what we scrape off of our cars when we have to scrape in the morning overnight. The water vapor in the air freezes directly to the glass on our windshields, and in this case in windows, and it's releasing 680 calories per gram of energy. So we have to make sure we're paying attention to what phase we're traveling from. Are we going from a solid to a liquid to a gas? Are we going gas to liquid, liquid to solid? Are we going from a solid to a gas, or are we going from a gas directly to a solid? At the end of the day, the net difference is going to be the amount of calories needed to be absorbed or released to go through the proper phase change. So let's look at the heating curve for water. This is what we worked on here today. So let's make sense of this. Your x-axis is time, and your y-axis is change in temperature. But be careful here, because if I call this red area, I'll call this number 1. The temperature is changing. Adding heat to ice changes its temperature. Well, at least it's showing this on the graph. Well, it's actually showing negative 20. But we'll say to 0 degrees C. Yet it's still in the form of a crystalline solid. That's the solid state of ice. So this red here is changing temperature, but it's always in the solid state. 2 is this blue line right here, this is a phase change. This is called the latent heat of fusion. The temperature does not change. Heat energy is overcoming the molecular attraction to one another, destroying the 3D crystalline structure. It can be in both states, both a solid and a liquid at once. But it takes energy, it takes heat energy added to it to go through this phase change. And then location here, call this location 3, the temperature change. The liquid water must rise to 100 degrees Celsius. This often takes a while due to the water's high specific heat, the liquid state only. So this whole phase right here is changing temperature. Notice we get a slope. We have this slope here is going to be much, much steeper, as you'll see, than our slopes of this location and this location. So once we get to this point, we go through a process called the latent heat of vaporization, or water does. The temperature is not changing. Heat energy has to overcome the molecular attraction of liquid water from being close together to far apart. In this, actually, we can find both states. We can find both liquid and vapor or gas here. And lastly, location 5, the red line here. Temperature change. This is water vapor. We generally see steam not because we see water vapor. Water vapor is actually invisible, but because we see water vapor condensing back into its liquid state. So in this process, heat is given back to the atmosphere around where the water vapor is condensing. Steam burns are more severe than water burns. We'll talk about that here in just a second, right here. So let's go back and look at these in terms of numbers. So number 1, 2, 3, 4, and 5. Number 1, the ice has to change its temperature. It goes from some temperature to 0 degrees, where then it begins acquiring heat energy. But it's simply just changing its phase from a solid to a liquid. And this is where the latent heat comes into play. So location 2, the ice melts at 0 degrees Celsius, the latent heat of fusion. The temperature is not changing, it's simply just at its melting point. And that during this time, the heat energy has overcome the molecular attraction. Right? We're destroying solid ice and redistributing those molecules as having more kinetic energy in the form of a liquid. Notice location 3, it's completely a liquid, and it's going to rise in temperature. And you'll see that this slope is going to be much greater than the individual slopes here and the individual slopes here. Notice, so number 4 is then the liquid state is then moving into boiling or vaporizing. This is called the heat of vaporization. Adding or subtracting heat changes the temperature of the water. It's simply the kinetic energy average. Energy is used to overcome the molecules' attraction of one another, and this is changing their average kinetic energies. So notice at locations 2 and 4, these are where we find latent heat of fusion and latent heat of vaporization. That adding heat is not changing its temperature. It is increasing in the total heat energy, but it's not changing temperature. Therefore, we don't see any slope or rise or simply a change in my y-axis. That's very important. So 2 and 4 are my latent heat locations. And location number 5, the vapor increases in temperature from 100 plus degrees C. It's water vapor only, that the heat within the steam is much greater than the heat within water at 100 degrees C. So water at 100 degrees C and steam have different amounts of heat, even at the same temperature. That water at 100 degrees C still needs to have 600 calories of heat added to change the phase from the liquid to the gas. And this is why steam burns are much more severe than water burns. Steam just has much more heat energy within it than liquid water at 100 degrees C. So now we're going to add a couple elements to this. We need to make sense of this, and this is key. So where is water, or H2O, a solid, a liquid, and a gas? Well, it depends on where you look in the graph. So location 1 is always a solid, and location 3 is always a liquid, and location 5 is always a gas. But let's go back to where we find our latent heat, our phase changes, location 2 and 4. If I look at from A to B, let me rewind that. If I go back to look at just A is always a solid, whereas B is always a liquid. But from A to B, you're actually getting both a solid and a liquid. The molecular structure is being broken or formed, depending on which direction you're traveling on the graph, as it goes through a phase change. So if I'm traveling upwards, A is, well, it's always a solid, but from A to B, it's going to have both phases. And B is always going to be a liquid. If I go, then I look at location C. C is always a liquid, and D is always a gas. But C to D, anywhere in here, you're going to have both a liquid and a gas. The molecular structure is being broken, right? It's being broken as we move up, or it's being formed if I move my way down, going through its phase changes. So 2 and 4 are simply the latent heat of energy, whether I'm talking latent heat of fusion or latent heat of vaporization, in order to go through this phase change. Very, very key idea there. So let's make sense of the data we did from class here. And numbers 1 and 2 you can see on a prior slide, and it was on this slide right here. So you can kind of pause this and check and make sure you have that. But number 3, temperature changed very slowly when it looks at the ice itself before increasing the rate of temperature change of the liquid water. Very important here. We'll talk about that here in a moment. So here are the numbers I got from my own data. So I had done this lab. So this may not be exactly like yours, but you're going to use your group data to make calculations. So the average rate of change of temperature, my temperatures went from 0.2 degrees C to 3.8 degrees C in 3 minutes. So I took the difference, 3.8 minus 0.2 divided by 3, and I got about 1.2 degrees C per minute. That was the change in temperature. But then after it was melted, it went from about 4.5 degrees to 96 degrees in 8 minutes. And I find that the average rate was about 11.4 degrees C. Notice a much, much greater slope here. And therefore, the average rate after boiling was even slower yet. It went from 97.2 to about 99.9 degrees C in about 3 minutes. So let's make sense of what's happening with the changes in these temperatures. So in order to melt the ice, latent heat must be added to the ice in order to break the bonds. So this takes time, as energy is added to the ice. It must break the crystal structure apart. It's by adding kinetic energy. And we see that the rate of melting is slow, about 1.2 degrees per Celsius per minute. That's where my data here comes in. But then the water heats up at a greater rate, right, at 11.4 degrees C per minute, because the energy goes into temperature change, and no latent heat is required for this. So it's going to have a much greater rate of change. And then the average rate is slowed even further due to requiring much more latent heat required to break the liquid into a gas. And that was 0.9 degrees C per minute. And I can go back and I can show this, that this is going to have a slightly greater slope. And this is going to have a much, much lower slope. And in this case, in the process here, we can make sense as to why these changes in temperatures are simply going to be a function of the slope of what we have going on here. So the average slope here is going to be a small slope. This is going to be a much steeper slope because the rate of change was much, much greater. And then here to here is going to be even slower yet because my latent heat of vaporization takes a lot more heat energy in to break the water's molecular cohesive attraction of one another to have it become a gas in the form of water vapor. Hopefully that makes sense.